Hello, my name is Sharvin Sivakumar. My metric number is CD240031. Okay, today I am going to talk about the introduction. The study of the vibrating system is fundamental in engineering as it helps predict how structure and mechanical components respond to dynamic loads. In this experiment, the behavior of an undamped beam spring system is investigated to understand the relationship between spring stiffness, load, and natural frequency. By applying different weights to the three types of spring, the spring constants are determined from the force, elongation characteristics, and the effect of varying stiffness and spring attachment position on the beam's oscillation are examined. The analysis provides a baseline for understanding real vibration system and highlights the importance of spring properties in controlling motion, preventing renaissance, and ensuring the stability and reliability of mechanical and structure designs. Thank you.
Hi, I will proceed with methodology. For this experiment, we use experimental method to understand the concept of UMDAPED beam oscillation. So, for the first experiment, to determine the spring deflection coefficient, the step to do this experiment is to set the apparatus was set up in figure in the TM150 universal vibration apparatus, and then the length of spring K1 were measured without any load, and then a 200 gram load were attached at the spring end and the length of the spring were measured. This step were repeated by adding another 200 gram were added to the spring and the length of the spring were measured. This step were repeated until 800 gram of weight were added on the spring. Then, this procedure were repeated for the springs K2 and K3. And finally, the observation and data was recorded. For the next experiment, the second experiment is to determine the natural frequency of beam. The apparatus was set up as in figure in the TM115 universal vibration apparatus. The end of springs were attached to the lever arm at a distance of 350 mm from the lever end. Then, the lever arm were levered with the spring attached. The gray paper were arranged at the center of the marker. The power was switched on. The lever arm were pulled and released. At the same time, the motor was switched on and to let it operate at the paper grade, and 10 oscillations were recorded. The procedure was repeated by changing the distance of the spring position to 650 mm from the lever end, and the procedure was repeated from the beginning by using a different type of spring K2 and K3, and the experiment were observed and data was recorded.
Good morning, Doctor. My name is Nichan Jasing and I'm from Group 5. And the topic we are going to present is the undamped beam oscillation, and for my part is the observation part. So during the first experiment, we have three different types of spring. So each spring has different lengths, and for example, the first string is 72.1 mm, the second one is 73.6 mm, and the third one is 75.8 mm. So a different load is attached to the spring ranging between 200 to 800 grams, and this load is increased slowly when attached to the spring. So when the spring reaches its equilibrium condition, the elongation of each spring is measured and tabulated in the data for corresponding loads. It is also observed that the longer spring has elongated more compared with shorter springs. So moving on to the second experiment, the location of spring is changed to a distance of 350 mm and 650 mm. So the frequency is obtained using different location of the spring attached to the beam, and the result is recorded. So obviously, the spring must be properly aligned to ensure the beam is in equilibrium condition. And the pencil on the oscillator must also be fully tightened in order to avoid any motion which will interrupt the recording of the data. So that's all from me. Thank you very much.
Good evening, Doctor. I'm Ng Bin Qi with the metric number 823022, and I'm from the Group 5. Today, I'm going to present about the result for our title, undamped beam oscillation. And as we can see from the slide, we have the three type of spring, which is have the initial length with 72.1 mm, 73.6 mm, 75.8 mm. These are three type of spring, and they have the different. They all three of them, take the same weight with the 200 gram, 400 gram, 600 gram, 800 gram. This is the four times we take, and the elongation we take the maximum only lah, just the for 800 gram, and the K1 is take the 1.1 elongation mm and K2 is 3.8 elongation mm, and K3 is 18.1 mm. In this table, we can conclude that the K1 is the most stiffness spring than the other spring, then the other two spring, and yeah, this is the most stiffness one lah. Okay, so this is the for the first table. Thank you. Okay, so I will continue to talking about the next two table with the result. And the first table is related with the effect of spring thickness on the natural frequency of the beam. And if we can see that we have the six sample, and but with the difference of the length of level from the 350 mm to the 650 mm. And the natural frequency is for the first two sample is not detected because this is too close and no oscillation occur. And for the maximum sample, which is at the 650 mm, we got the natural frequency with the 16.67 hertz. Yeah. So for the next table, which is including the theoretical and experimental natural frequency of the beam. And this table is mostly talking about comparison with the theoretical and the experimental result. And from the table, we can conclude that the sample 6 is mostly close to our theoretical result, which is this only have the, I think it's from our calculation is a 2% only the deviation and for the other sample from 3 to 5, it's mostly a little bit deviation, a bigger deviation compared to the sample 6. Yeah, thank you. This is for the result part. Yeah, it's me again. I will continue to talk about the discussion for the previous table. So for the first one, the table is talking about the stiffness of the spring, and in conclusion, the K1 exhibit the highest stiffness, which is low deflection because it have the smallest elongation only, right? And the K3 exhibit the lowest stiffness because it have the active 18.1 and an elongation is a large difference before compared to the original length of that. For the second table, which is talking about the oscillation and the natural frequency, and for the level, in conclusion, the level length is increasing the level length. The level length increase from 350 mm to 650 mm result in a higher natural frequency across all sample. And the spring constant, the change in spring type significantly shift the system oscillation frequency, which means when the spring is the more stiffness, the natural frequency will more lower. Yeah. So for the third one, with the comparison of the theoretical data and the experimental data, experimental natural frequency was compared against theoretical natural frequency, and the experimental result closely track the theoretical values validating the beam. And the sample 5 showed high accuracy with a deviation of less than 2%. Yeah, as I just said before at the result part. Yeah. So this is our discussion that conclude that the spring stiffness is directly effect to the natural frequency of the data. Yeah, thank you for that.